You know what? I talk to a lot of people, and I gotta say, I have an easier time talking to grown-ups than kids. Does that surprise you?
No.
Alright, so you guys are gonna be nice to me, right?
No. Yes.
Okay.
No.
My name is Graham Garner. I'm the Vice President for Advancement at the School of Mines. And what that really means as far as you guys are interested is I get to work with the relationships that we have with people outside of the school. So we work with the media. Brianna over here, she works with reporters from TV and newspapers. She helps them get what they need. Mitch Vandervorst back here, he does some of that same stuff. He also gets a lot of things up for us on our Facebook page and YouTube and Twitter and lots of other things that he does. John Michaels back here is our photographer, videographer, designer. He does a lot of that kind of stuff. So we're kind of the team that does a lot of design and community relations, so we kind of like to be involved with you. And we want you to know how important science and technology are. In fact, I'll tell you somebody who really cares a great deal about that is our president, Bob Wharton. He's the president of the School of Mines. And hopefully you guys will get to know him better. How many of you guys like science? I bet Mrs. Keegan's watching. Yeah. Great, good. Well, and you know, we have many other special guests with us here today, and so I'm going to let them, I'm not going to take a lot of time talking, I'm going to let them talk to you a little bit about why science is important and how you guys can go from what you're doing today to building something like what you see over here with Eric and Ronik, and they'll tell you more about that, and then of course Dr. Squyres with the Rover on Mars, so I'm sure you'd be very interested to hear that. Yes. I'm sorry, I don't know.
Dr. Mitchell. He's our
School.
Great, good to have you here.
Old science teacher.
Excellent, excellent. So there's lots of things you guys can do in your future. It's really up to you, what you're excited about and what you're willing to spend some work on. And these guys are going to say a little bit about that. So I think we'll turn time over to Eric and Ronik now.
Okay, so my name is Ronik Bhushan. I am a grad student at the School of Mines. I'm doing my master's in engineering management. I have my undergrad from the School of Mines again in industrial engineering, and I love science and math all the way through school. I'll let Eric introduce himself.
My name is Eric Kuipers. I'm doing graduate school, the same as Ronik, in a mechanical engineering. I've been doing school at Tech for probably the last 7 years, and it's fun stuff. I get to play with kids every day. You know, I get to play with all this math and science stuff and apply it to stuff like that. You know, it's very cool stuff. So, what we're going to try to do is kind of explain to you what we do a little bit and kind of apply it back to you guys.
Yep. So Eric and I are both members of the unmanned aerial vehicle team. Eric is the chief engineer, I'm the team manager of the team. How many of you know what an unmanned aerial vehicle is? Yes?
Something like the planes that they use in the military.
Yep. Kind of. What we do is a little bit different from that. Have you guys ever played with remote control helicopters?
Yeah.
Okay, so you've all seen those. What we do is kind of like that, but we use a little bigger helicopters, and what we do is make them fly themselves. Our goal is to make it intelligent so that it can go through your hallways and find offices on its own. Kind of scary?
No.
Can you think of reasons why you would want to do something like that?
To spy.
If the doorbell rings, it can come get you.
Say, what if the building was on fire and a lot of people escaped, but you knew a couple of people were left inside? But it's too dangerous to send a human being in, so what do? You send a robot in. And it says, okay, we know somebody's in here, we know which window to get into and get a person out. So that's what unmanned aerial vehicles are. What we do is we go to a competition. It's an international competition. It's called the International Aerial Robotics Competition. And I'll let Eric talk a little bit about what we had to do at that competition.
Yeah, the competition that we go to last year was actually down in Puerto Rico, so we got to travel a little bit to go see somewhere new. But at this competition, basically what we had to do was like a James Bond spy mission. Like we had to go into a window, all autonomously. We push a button, let it go and do its own thing. We had to go into a window, navigate through a hallway, map out what's actually there so that thing has to sense and know what's going on. It's just like a person if they walked into a dark room. How do you know what's around you? You have to feel around and you can kind of sense where you're doing. That's what our robot does. It senses and maps out what's going on. Basically because it has a small brain. And what it does, after that we have to go and find a sign on a door for the chief of security in a different language. We have to go find it in an Arabic language to note or locate this door. Once we get in that door, we have to go and pick up a little USB jump drive and then drop off the replacement. And we have to do this all in 10 minutes. So it's a pretty complicated little thing that we have to do, and it's what keeps us busy, and that's what we see over here is what we've done for the last year and a half, is try to beat that competition. So that's our little spy robot for the most part.
Yeah. What our competition does, essentially, when they give us this mission, they tell us, given what technology is available, it cannot be done. So we have to go and invent a solution to solve a problem that doesn't have a solution right now. So with this, now, we took this to competition last year, and what it does, now the propellers obviously spin. They spin in opposite directions to each other so that they can counter the spin of the entire system. And it can go, if it wants to go forward, it spins out the back, reduces the thrust in the front, and it tilts forward and goes forward. And so, in the same way, it can go in all directions. In order for it to see where it's going, it has a camera on the back. So what it can do with this is, it can read the sign that Eric talked about. It can look for a camera watching. There's a laser line, like a line barrier that it has to find and see and tell us, okay, there's a barrier up there, we don't want to trip the alarm. And what we also have up top here, now, does anybody know or have ever seen anything that looks like this up here? Any guesses? You guys back there?
It's a speaker that like detects if someone's talking or not.
What it is a spinning laser. Do you know what radar is?
Yeah.
You've seen the radar towers at airports, right? What radar does is it sends sound out, and based on the sound bouncing back, it can tell where objects are. What this is, it's a laser, and the laser spins 10 times a second and sends this laser beam all around the room, and what it can do is tell how far an object is at any given spot around the circle here. So while it's spinning, it can draw out a map of this entire room, and so it knows better than you could say that that wall is a certain very specific distance away from it. So if it's facing this way, it knows this wall's here, and it knows it can't go forward. So it builds a map for itself and flies through the entire building. Now it's not as easy as for us to just basically say, we know we need to go down this hallway, it's this long, turn left at this hallway, that's where our room is. We aren't allowed to see this building at all. The first thing that sees the inside of the building is this robot, and it has to figure its way out. So, any questions on how any of this works? Yes?
Not to that point yet. Someday.
That's a good question.
Because somebody could throw a string up.
Net.
Let's
Yeah.
watch it.
Any questions?
Will you turn it on?
Not in here.
Outside?
And
It's
not
a
around
little
us.
scary.
It's a little scary. Even, to be honest, we work with it a lot. It scares us. And part of being a scientist or an engineer is having to be safe and responsible with what you're working on. And so we have to be very careful with how we're working, because these things spin really fast. They can cut your fingers,
They hurt. Trust
they
me.
hurt, and they can break a lot of stuff. So we're not going to fly them here. You have a question?
Yeah, how long did it take to build it?
It has been on for years now. I've been on the team for 5 years, I think, and we've been working on it ever since then. And as students, obviously, we have to go to class, and we have to pay attention there. So when we have free time, we get to work on projects like this. Question?
What do you think the expenses are?
It's hard to tell. We were just trying to talk about this before coming here, and we can tell you the cost of the parts on here, but in actual terms of people are paid to work on this. And so if you really added it up, it probably costs between $50,000 and $100,000.
For the time put into that. We
So-
have different components on it. The biggest thing is like, you can see there's a little computer on there. You guys ever seen those tiny little notebook computers? Basically, that's the same computer that's in those little notebooks.
We've actually hooked this up to a screen and surfed the web with it, with a helicopter.
Are the propellers metal or are they plastic?
So what did you say?
Are the propellers metal or are they plastic?
Okay, he asked if the propellers were metal or plastic. These are plastic, and they normally are plastic. And you have different kinds of properties that in your science classes you get to learn how different materials will flex, bend. If metal could be pretty dangerous. It's like a knife spinning really, really fast.
Let's take one more question.
Does the radar detect people?
Yes, it can. Any object around its range of detection, it will see. And so for the moment where we are with it is it can detect things that are not moving. So if you move up in front of it, it's going to get confused. So when we're flying, we have to make sure nobody is in the field of view of it.
How do you pick up the jump drive?
This arm up here, you're probably seeing this swinging up and down while I'm talking. This has magnets on it. And a thumb drive, obviously you know, the tip is metal. So what the camera does, we have a camera back here, it actually goes up front here, but we mounted it back there for today. It can see where the thumb drive is on a table. Then when it sees it, it knows, okay, I need to fly in this certain direction, head towards it. This arm swings out, and underneath here we have a whole bunch of really strong magnets. So it swings out, and then does a slide across the table, picks up the thumb drive. What you have here is an electromagnet, which holds on to a decoy thumb drive. So when it knows it's picked up the other thumb drive, it just sends a signal to the electromagnet saying, let go. It drops off the other thumb drive on the table. Mission's done. Fly out. It has to fly back out, avoiding again the cameras and the laser barriers. And all has to be done in 10 minutes. So, if you...
Let's give Eric and Ronica a hand. How many of you think you'd be interested in learning how to put something like that together? It's pretty interesting, isn't it? You guys are on the right path to doing that. Do well in science, do well in math, have a great imagination, and you're on your way. And I'm sure that, now Dr. Squyres, I'm sure you guys have all seen Roving Mars, right? You guys all saw it. So I don't probably need to give you a very long introduction to Dr. Squyres. I'll leave him more time to talk. But I'm sure that at some point he was in a classroom like this. He was someone like you, and probably college. Maybe he wasn't doing these things. He's a geologist, but he realized that this could help him do some of the things that he was interested in learning about. So let's give a hand to Dr. Squyres.
Thanks. Well, it's nice to be here. Let's see. I didn't bring my robots with me. I couldn't bring them. They don't fly, at least not anymore. They used to, but they don't fly now. They're not nearly as smart as this one, but they're on Mars, so that's cool. Yeah, so you've seen the movie. You know more or less what we do. If you went to Mars, you would absolutely hate it. It's a terrible, terrible place. It's cold, it's dry, it's dreary, it's beautiful, but it's not a nice place. And it would be a tough place for humans. It would be a tough place for any kind of life. But what we wanted to learn, and this is what got me started in all this. As he said, I started off as a geologist, and a geologist is sort of like a detective. At the scene of a crime, you know, you're looking at clues, and the clues are in the rocks. What you do is you look at the rocks and you try to figure out what was it like when this rock was made. So like, for example, just a real simple example, let's say you've got a river that is carrying stuff and dumping it into a lake somewhere. And it might be carrying coarse grains and little fine grains of silt and so forth. And if you find a rock that's made of really coarse grains, like coarse grains of sand, that means that it was deposited where the river first emptied into the lake, and it drops the coarse grain sediments right away. But the little fine ones, they'll settle out in deeper water. So just by looking at how big the grains are, you can tell was it deep water, was it shallow water. And there's lots of other stuff like that too. So what we wanted to do was go to Mars. I mean, I want to go myself, right? I want to go to Mars myself. That's what I wish I could do. I can't. In fact, the very first people who are going to go to Mars are not astronauts. Not today. They are in high school or middle school. Okay, that's going to happen 30 years from now. So you guys are the right age to go to Mars. I'm too old. I can't go. So what I had to do is build robots instead. So what we did was we designed a couple of high-tech robots. Let's see, they're about this tall, so about the same height that you are. They've got eyes. Their eyes are a little further apart than yours. They're about this far apart. They take pictures just like the picture, like the camera does on that robot there. They got 6 wheels, so they can drive across the countryside. They've got an arm. There's an arm on the front of it that's got a shoulder and an elbow and a wrist. It's basically the same dimensions as my arm. and it's got a microscope on it and a drill and tools for looking at the rocks. And they're basically robot explorers. And what we do is we use them to explore Mars. So here's how it works. What I'd like to do, you know, what I wish I could do would be to joystick the thing, right? What I'd like to be able to do is sit in my office and steer it around rocks and that kind of stuff. But we can't do that. Mars is incredibly far away. Like 100 million miles is a typical distance between Earth and Mars. So when we send a radio signal telling our robot what to do, that radio signal travels at the speed of light, as fast as anything can travel, from Earth to Mars, but it takes like 10 minutes to get there. And then something happens on Mars, and 10 minutes for a radio signal to get back. You can't joystick something because there's too much of a time delay. So what we've done instead is give our robots vision and the ability to kind of make their own decisions. It's sort of like what this thing does. They can look at the terrain in front of them, and let's say the rover's driving along, and it's driving along, and then it sees a scary rock. Okay? It'll look at that rock and figure out how big it is and figure out, can I drive over this? No, I got to go around it. Right? And we can actually program different levels of courage or cowardice into the rovers depending on how difficult and dangerous we think the terrain is. And we tell the rovers what to do. And so every day we sit down and we look at the latest pictures that came down from Mars, and we decide, okay, where do we want to go today? We want to drive over and climb this hill, and we want to take pictures, or we want to reach out with the arm and take a picture with our microscope of some rocks we see in front of us, and what have you. And we've been doing this for 6.5 years now. The rovers landed on Mars in January of 2004. We designed them to last for 3 months, and it's been 6.5 years, and they're still going, we're still operating them. And we have found some pretty cool stuff. What we have learned is that even though Mars is really, really cold and dry and miserable today, billions of years ago, it was different. There was water. There was water below the ground, there was water that came up to the surface, there were hot springs, yeah.
Was the water drinkable?
That's a really good question. Was the water drinkable? Most of it was not. Most of it you would not have wanted to drink, and we can tell that. When minerals form in rocks, you can look at the minerals and you can figure out what the chemistry of the water was like. And it turns out that the water at most of the places that we've been to was actually acid. So people say, oh yeah, the rovers discovered evidence of water on Mars. Actually what we discovered the evidence of was sulfuric acid on Mars. But actually there are organisms, there are microorganisms that can live in that stuff. In fact, that love living in that stuff. There are places on Earth where the groundwater is very acid, and yet there are microbes that thrive in that stuff. They're called acidophiles, acid lovers, and they actually live in those kinds of conditions. So it would have been a tough place for life, but there are places where we found, actually there are places where we found evidence for water that probably would have been drinkable. One outcrop we found had rock that was basically made of limestone. And that wouldn't form an acid. That says that the water was probably drinkable. But no, for the most part, it was pretty nasty stuff. That's a good question. So anyway, that's what we do. Yeah, question.
How come we didn't send a rover to the ice cap?
How come we didn't send a rover? That's a really good question. Why didn't we send a rover to the ice cap? The reason is that our rovers are solar powered. They get their electrical energy from the sun. And when you go real high to the northern latitudes or down near the South Pole, the sun is so low in the sky, you don't have enough electrical power, and the rover would kind of freeze and die. So because we have solar-powered vehicles, we had to land pretty close to the equator. So let me just say a little bit of how I got started in this. I grew up in New Jersey, southern New Jersey, went to elementary school, middle school, high school there. When I was your age, I just loved science, every kind of science. Biology, geology, physics, everything, you name it, chemistry. I was really into all that kind of stuff. And the other thing that I really liked doing was climbing mountains. I was really, really into climbing mountains. In fact, those are still my two favorite things, is science and climbing mountains. And so I decided, well, if I like doing science and I like climbing mountains, I should pick a kind of science you can do in the mountains. So I decided to become a geologist. And when I went to college, studying geology. I really liked it, but I just, you know, I wanted something a little different. And then this was back in the days when there was a mission to Mars called the Viking mission. Anybody ever heard of Viking? It was a lander to land on Mars. Yeah. And I took a course from some people who worked on that mission, and I just thought space exploration was really cool. I wanted to go to Mars myself. I still want to go to Mars myself, and I can't. But what I realized was that you could do geology on Mars if you could build a robot that was capable of doing the stuff we wanted to do. So I started learning about engineering. I learned about robotics, and I learned about electrical engineering and mechanical engineering and all the kind of stuff that these guys do. I mean, these guys are trained engineers. I'm kind of a pretend engineer. I just kind of pick the stuff up on the side. But I've been doing that stuff ever since. And, you know, the reason I'm doing rovers on Mars basically is because it's the most fun thing I could possibly think of to do. If I could think of anything more fun than operating a robot on another planet, I'd be doing that instead. So we feel really, really lucky to be able to do what we do. And the thing that I think excites me most about it is not what we can do with these rovers, but what future missions to Mars are going to be like. The kind of stuff that's going to be happening. You guys are, you know, my age. We're going to be sending humans to Mars. We're going to be sending robots to fantastic places. I'll tell you one of my favorites. There's a moon of Jupiter. It's called Europa. Great big thing. It's about the size of the Earth's moon. It has a crust of ice that's probably miles thick. And underneath that ice is an ocean of liquid water. There are two oceans in the solar system. Earth has one. Europa has the other. Is there anything living in that ocean? I would love to know. So, I mean, you got the job of building a robot that is able to go through a window and fly down a hallway and find a sign on a door and pick up a jump drive and bring it back out. Imagine if your job is to build a robot that's going to go to Jupiter, land on one of the moons of Jupiter, melt its way down through 5 miles of ice, swim down into an ocean by itself and discover if there's life there. That's a challenge. So these guys are too old. They're not going to get to do that. I certainly not going to do it. You guys are the right age to do that kind of stuff. So I'm actually, while I think what we're doing right now is very cool, I'm actually very envious of you guys, because you're going to get to do stuff that's way, way, way cooler than what we get to do. Yeah?
In the movie,
Yeah.
you called the Rovers boys, and then you called them girls.
No, it was always girls. There were never boys.
Okay.
They're always girls. They're both female, Spirit and Opportunity. They're both called she, and I don't know why. I think it's for the same reason that you know, sailors call their ships she. That's just the way we've always done it. Right here.
What happens if the rover flips over?
What happens if the rover flips over? I have a very bad day. Yeah, there's no way to flip them back right side up. If they flip over, they are dead, and that's the end of the mission. So we try very hard to make sure that that doesn't happen. Yeah.
What are the parachutes made?
The parachutes are made of nylon, just pretty much normal, you know, fabric that you would use. There's nothing particularly tricky about the fabric that we use. Right here.
Why did you name the rover Spirit?
Why did we name the rover Spirit and Opportunity? What we actually did was it was sort of like a contest. Before we built the rovers, we had an activity where students in middle schools and elementary schools were asked to suggest a pair of names for the rovers. And we had tens of thousands of suggestions. And the winning suggestion, the one that was picked, was it was written by, I think she was about 8 or 9 years old. Her name was Sophie Collis. She was from Arizona. This was a girl who had been born in Russia, and she had lived the first 4 or 5 years of her life in an orphanage in Russia. And then she had been adopted by an American family, came to the United States, and she suggested those names, Spirit and Opportunity, because they sort of reminded her of her experience coming to the United States and being able to live here. I thought they were pretty nice names. Yeah? Why did we wear the white suits? Yeah, those crazy looking white suits. The reason we wore those was to keep the rovers clean. You know, humans, you have grease on your fingertips, you got dandruff, you know, humans are dirty things, right? And we didn't want to get any contamination on the rovers. We didn't, they've got very sensitive equipment, cameras and optics and sensors and so forth. We wanted to keep very clean. Also, suppose you're going to someday send a spacecraft to Mars to learn if there's life there. You don't want to send life with you. I mean, we got bacteria on our hands and that kind of stuff. So we tried to keep the rovers very, very, very clean when we built them. Now, the irony of that, when I look at the rovers today, is today the rovers are filthy, covered with dirt, dust, and all scratched up and beat up. But at least it's Martian. Here.
Are the Spirit and Opportunity in the same, where are they at?
They're on completely opposite sides of the planet. They're like 180 degrees apart, almost as far apart as you can be on Mars. Right here.
Why don't we send rovers to other planets?
Why don't we send rovers to other planets? Rovers have been sent to some other places. Rovers have been sent to the moon, for example, back in the 70s. The Russians did that. There are some places that are tough for rovers, like the surface of Venus is really, really hot. Jupiter, Saturn, Uranus, Neptune, the big planets in the outer solar system, they don't even have solid surfaces, so there's no place to drive around. You don't want an airplane there, maybe a balloon. But you know, there are like, I mentioned that moon Europa, that's a place where you could send a rover if you wanted to, though probably what you really want to send is a submarine. Right here.
How did the rover get its name?
Well, that was the question I answered earlier. There was this contest where we had people suggest names for rovers. Right here.
Why Mars? Why did you guys choose Mars?
Why Mars? That's a good question. The reason that I focused on Mars is kind of a combination of two things. One is that it's a really interesting place. I mean, like Venus, interesting, but the surface temperature is 700 degrees. I mean, it's hot enough to melt lead. So there was never going to be life on Venus. I chose Mars partly because it's enough like Earth that you can imagine life having taken hold there. The other reason I picked Mars, frankly, was just practical stuff. You know, if I could figure out how to do this submarine on Europa mission, I wouldn't be messing around with rovers on Mars. But submarines on Europa are too hard for me. At least rovers on Mars I know how to do, so it was partly that too. Right here. How fast do the rovers go? Pedal to the metal, fast as they can go, 6 centimeters a second. They're really, really slow. And it's actually worse than that, because what happens is, like I said, they go driving along, and then they have to stop and look at the rocks in front of them and think and think and think and think and think and think and decide, can I go around that rock or do I, can I go over it? And the computer in the rover is way, way, way slower than the computer in that helicopter, and it takes them a long time to make decisions. So if you were watching these rovers, you would get really bored really fast. They're extremely slow. Right here.
Does it make you impatient to watch them?
Oh, gosh, does it make me impatient? Yes. Yes, it drives me crazy. I mean, okay, Dr. Wharton over there, Bob Wharton, he and I have done field work together in the Antarctic. He and I have worked in Antarctica together and done field work, and we do geology and other stuff. And what Spirit and Opportunity have done in 6.5 years, Bob and I could have done in a good week, I think. It is excruciatingly slow, and it drives me crazy. But they are on Mars, so, you deal with it. Yeah?
Well, how did you feel when they found signal?
How did I feel? Mostly relieved. What the movie didn't really show was all the many, many years that went into creating these things. And this is another important message, guys. I started working on these things in 1987, long before you were born. And it took me 10 years writing proposals to NASA just to try to convince them to do this. And I wrote a proposal and they rejected it. And 3 years later I'd write another proposal and they rejected it. That happened 4 times before they finally said yes. And then after they said yes, they canceled us 3 times. Came back to life each time. They said, yeah, we're really going to do this in the year 2000. It was 16 years just to get those rovers to the launch pad in Florida. So when those things were landing, my heart was in my throat the whole time. I mean, you hit the top of the Martian atmosphere going 27 times the speed of sound, and 6 minutes later you're on the Martian surface. And either it works or they're just busted into pieces, and you don't know. So, yeah, I was relieved. I was just relieved because I was facing the prospect that 16 years of my career had been totally wasted if they didn't survive that landing. It felt really good. Way in the back.
Isn't there a plan to send a rover to Mercury?
Rover to Mercury. We haven't talked about rovers to Mercury. We have talked about landers on Mercury. Mercury is an interesting place. It's so close to the sun, you'd think it would be extremely hot, and in fact it is. But near the poles of Mercury, there are places where there are craters that sunlight can never get into. And so it's actually quite cold inside these craters, and we think there's ice inside those craters. And so there has been talk about sending a lander to the polar regions on Mercury to see if there's really ice there. But we haven't talked about a rover. I guess you could probably do it, but it would be tough. It's a very difficult environment. Yeah.
I just forgot the question.
Okay, right here. Will we make more rovers after Spirit Opportunity? There is actually a new rover. Its name is Curiosity, that is going to be launched to Mars in November of next year. It's a bigger vehicle, it's nuclear powered, it's got all sorts of cool instruments on it, so yeah, we're going to keep building rovers.
When you sent the rovers to Mars, how many airbags?
Airbags, oh gosh, jeez. Yeah, I've been doing talks about these rovers for years, and no one's ever asked me how many airbags there are. Let me count them, see if I can count them. 24. 24 airbags. Yeah. Great question. Nobody ever asked me that. A single airbag is like this big. I mean, the complete cluster of airbags around the vehicle is huge. It's really, really big. Yeah. Do you think there ever will be life on Mars? Absolutely. We're going to send humans to Mars, and then there will be life there. So we're going to take it. Yeah.
How many hours a day Mars works on the rover?
How many hours a day did we work on the rover? It varied depending on when we were, where we were in the development of these things. But once we got down to the end, I mean, the stuff that you saw in the movie where we were actually physically building those things, for a while we were working 2 shifts a day, so 16 hours, and then towards the end we went to 3 shifts, so 24 hours round the clock. We had people working on them. And I was putting in a lot of 12, 14-hour days myself. Yeah.
How many tests do you have to do on the rover?
How many tests did we have to do? Thousands and thousands and thousands of tests. It's all about testing. These guys will tell you the same thing. And the first time you test anything, it doesn't work. The first time we tried to drive Spirit forward, it went backwards. I mean, just every test fails. But that's the way you learn. And so, yeah, it's all about testing. You test and you test and you test and you test. Right here.
Why did the rocket spin?
Oh, that's a great question. Why did the rocket spin? Yeah, if you look at the launch sequence, the third stage, the final stage, the one that sends it off to Mars, is spun up. And what that does is for stability. Because that final rocket motor, that's the thing that actually sends you on the trajectory to Mars. So you've got to have that rocket motor oriented just right in space. If it's tilted the wrong way, it's going to send you in the wrong direction. You're not going to get to Mars. So having it oriented properly is very important. You know about gyroscopes? You know what a gyroscope is? Gyroscope is something where you spin it and it'll sort of stay fixed in space. Basically, you turn the entire rocket into a gyroscope. You spin the entire thing. And what it does is it makes it stable so that it will have just the right orientation. It's a simple way to stabilize something. Instead of having a complicated little gyroscope system to stabilize it in a certain way, you just spin the whole thing and you make the whole spacecraft into one big gyroscope.
Do you have pictures of Olympus Mons?
Do we have pictures of Olympus Mons? We do not have pictures of Olympus Mons that we have taken from our rovers because the rovers landed very far away from Olympus Mons. They landed in other... Mars is a big planet. I mean, the total surface area of Mars is as big as all the continents of Earth combined. So Asia, Africa, North America, South America. It's a big place. But if you go online, you can find pictures of Olympus Mons that are taken from orbit, and they're just spectacular. Yeah, here.
Did you think Spirit was going to survive it?
Did I think Spirit was going to survive it? Yeah, you know, I did. I wasn't sure, and I was very nervous that it wouldn't. But I had a lot of confidence in the vehicles because I had so much confidence in the people who built them. We had an incredible team of people, 4,000 people worked to build those rovers. Smartest, most dedicated bunch of people I've ever worked together with in my life. I had so much confidence in those people that I really, really thought it was going to work. Now, you can always have what we call a bad day at the landing site. You know, you can have a gust of wind, or you can have some sharp, pointy rock that you just can't predict, and that could kill you. But you know, even though we looked really nervous, and I was during the landing, in my heart, I always believed that they were going to work. Yeah. Right here.
How long does it take to find gas things from?
I'm sorry, I don't understand the question.
Like the fuel?
Oh, the fuel for the rocket? The different parts of the rocket use different fuels, but we'll talk about the first stage. The first stage is the thing that, you know, really gets you going off the ground. There's fuel and there's oxidizers, so rockets have to carry both of those things. The fuel is just plain old kerosene, and we used a lot of kerosene that day. The oxidizer is something called liquid oxygen, very cold stuff. So we loaded the fuel into the rocket a couple days before launch, so it's there for about 48 hours before we launch. The liquid oxygen, because it boils off so rapidly, you have to put in right before you can use it. So we loaded the liquid oxygen only about 2 hours before we launched. Yeah.
Is there a chance that all the rovers that are on and going to be on Mars will ever meet?
No, you know, I wish that they could meet, but like I said, they're on opposite sides of the planet. So, like, you know, Mars is as big as all the continents combined. The rovers are on opposite sides of the planet, and Opportunity, which is the rover that has covered the most distance, has driven about 15 miles over its entire lifetime. Like I said, it's really slow, right? Okay. I mean, a really good day will drive about 100 yards. So, no, they were together in Florida at Cape Canaveral, and they're never going to see each other again. Yeah.
So when you if you believe people are gonna go to Mars, like,
Yeah.
why don't you make it so they can take samples of rocks and put them in their carriers, and then they just keep it, and then when you guys go and retrieve them.
Oh, okay. Yeah, yeah. One of the most important things that you really want to do at Mars is the mission that we call Mars Sample Return, where you actually bring rocks back from Mars. I would love to be able to do that. We are just now beginning to plan a mission like that. It's a phenomenally complicated mission. 3 parts. First part is a rover, very much like Spirit and Opportunity, that drives around but does exactly what you just suggested. Okay, instead of just looking at the rocks, it actually picks them up and it puts them into a little canister about this big. Okay. Next mission goes and lands alongside that, goes over and takes that canister of samples, puts it into the nose cone of a rocket that's about this tall, and shoots that rocket into orbit around Mars, putting into orbit around Mars a spacecraft about the size of a coconut that has the samples inside. Third mission flies to Mars, goes into orbit around Mars, finds that little coconut-sized spacecraft. There's another robotic task for you. Gathers it in and sends it back to Earth, where it comes and lands. Tough, tough mission to do, but I think we're going to do it in the next 20 years or so. Ultimately, when humans go to Mars, of course, they will bring samples back too. Right here.
Will Spirit and Opportunity still be alive?
Oh, Spirit and Opportunity are, well, let's see. Spirit is hibernating right now, and we hope is going to wake up. It's been wintertime on Mars, and Spirit is hibernating, and we hope we'll wake up very soon. Opportunity is alive and well. I was sending commands to Opportunity 3 days ago before I came out to South Dakota. And you can go online, you can go on the web, and you can see pictures that just came down from Mars today. So yeah, Opportunity is very busy and doing very, very well. Right here. Yeah, you.
Professor, did you go on the way to Mars?
how fast did we go on the way to Mars? That's a good question. It was about 300 million miles, and it took us 7 months to get there. So just doing the math roughly in my head, that probably works out to something like, I'm going to guess, 5 miles a second? Something like that. Oh yeah, it's fast. It's serious. I mean, you saw that rocket launch. It is seriously fast. Yeah, right here. Why did we use such a big door? The reason was that when you actually send the spacecraft out to the launch pad, the spacecraft itself is pretty big. I mean, the spacecraft would be like from me to her, okay, and like that tall, something like that. But then what we do is we stack the spacecraft on top of the third stage of the launch vehicle. So we actually bring the third stage of the rocket indoors, put the spacecraft on top of it, and then take the whole thing out the door. And it's just big, so you need a big door. Yeah?
You said how if Rover were to tip over
Yeah. That would be a bad day.
it would be bad of it.
Yeah.
Why don't you just put something on it to make it get back up?
Yeah, that's a good question. Why don't you put some kind of lever on it that would flip it right side up? You could do that. The problem is that would be a big, heavy, complicated mechanical device. Okay? And the thing that when you're building something like this, you can only make it just so heavy and no heavier. So like this thing here, those propellers have enough thrust to lift a certain amount of weight, but no more. And so they can I'm sure these guys can think of all sorts of cool things that they'd like to put on this thing, but they can't because the propellers can't lift that much weight. Same thing with our rocket. Rocket can only send so much weight to Mars, and so you have to be very thoughtful about what you carry and what you don't. You can't take everything you'd like. So instead of carrying those big heavy levers to flip the thing right side up, we just say, okay, let's not flip it upside down.
Okay, I think we got time for one more
One
question.
more. Oh gosh. You.
How much wear is on the robots when the elements on Mars?
How much wear? Oh boy, they're wearing out. You know, we designed them to last for 3 months. It's been 6.5 years, and these robots have a lot of moving parts. They got motors, they got gearboxes. So let's see. On Spirit, the right front wheel doesn't turn anymore. The right rear wheel doesn't turn anymore. So Spirit doesn't drive real well anymore. We got 6 wheels total. On Opportunity, the joint that moves the arm back and forth this way doesn't work anymore, so we can just do this with the arm. But of course, if we want to move the arm, we just move the whole everything, right? So we can do that. Do it that way. Let's see, what else is worn out? They're all just beat up. I mean, they're scratched and they're dirty. And they were beautiful things when we first built them, but we've used them pretty hard. I wish we could do this for hours, guys. This is a lot of fun. Are we done?
I think so.
Okay.
You guys enjoy it?
Great.